All right, so now let's talk about humidity and vapor pressure. So what is humidity? All right, so think about this. So let's say we take two different places. One is like a desert, a dry, another one, maybe one of those eastern or southern states, like Florida, for example. So one of the things we have, if you live in a desert, then when you sweat, because it's so dry, the sweat evaporates very quickly, and you then don't feel the hot as much. If you live somewhere like Florida, then what you have here is that there's humidity over there. It's a humid place. So when you sweat, it doesn't evaporate as quickly. So it stays with you and you feel it, or it feels like it's hotter than it sort of like hotter than it is. And sometimes you might even see that some of the weather reports say that, you know, it's 95, but it feels like 100. Why? Because of the humidity. Okay. So now, one of the things we're going to see here is that generally when your sweat evaporates, that's actually a cooling process. Your body cools down when that happens. So that's kind of like an example of humidity. So humidity has something to do with the amount of water vapor that is in the air. Okay. If there is a lot of water vapor in the air, it is hard for sweat to evaporate from you. And if the air is dry, where there's not much water, then it is easy for sweat to evaporate from you. And then you basically cool down. So again, you can think of like, let's say this cooling, right, is or evaporation, right, is a cooling process. Okay, now let's talk about then in terms of how we can understand this whole humidity process. So we're going to start with a container like this. So let's say we have a container with water. Okay. Now, in this container right now, we have, let's say it's evacuated, a container. That means we have water and vacuum. So that means this whole region here is vacuum. There's nothing there. Okay. Now, at this point, what we have here is we have just water molecules. Okay. So let's call this, you know, I don't know, let's call this state A. Okay. So this is state A where you have uh, just water molecules and nothing else. At this point, what we can say here is that in this region, right, so like let's say there are no other molecules. So basically at this point it doesn't contain any water vapor. Okay. So at some point at later time, then some of the water molecules, remember we talked about, right, so there are molecules that are moving faster than the average, there are moving, some of them moving slower than the average. So those ones that are closer to the surface and moving faster than the average can actually escape and evaporate. That means eventually what we will have here is we will have some of the molecules here in that region. Okay. Then what happens here is that when those molecules basically evaporate in this region, then they create what we call a partial pressure. Okay. So the partial pressure, let's call this PP, like P partial pressure, right? So this was for the case A, right? Basically, or state A, it was zero. That's because basically for state A, remember, right? We didn't have anything. There were no, let's say vapor molecules, right? No molecules over there. So the partial pressure was equals to zero. As those molecules start evaporating, then you can say, right, so now we have some molecules like this. Let's call this state B. So this is going to be B when you have now some molecules. So think like this. So right now this is B with some molecules. Okay. So when when you have then this water molecules already evaporating, that means you have sort of like, let's say, this from liquid to gas, right? Transition. So some of the molecules going from liquid to gas. Okay. So eventually what you have here is you have more and more, water molecules going from liquid to gas. But it's never just, one way highway. So like, let's say one way road. some of the, those molecules, right, those gas molecules can actually come back to become a liquid. So you can also have a liquid to a gas, sorry, gas to liquid. So you can also have gas to liquid going in opposite direction. Okay, so that means what we have here, this is then basically evaporation. So this process known as evaporation. And what you have here is that the inverse process, right, from gas to liquid is known as a condensation, right? So that's basically condensation. Okay. So you have condensation going from gas to liquid and evaporation. And in a way, you can say that state A is when you have no, let's say, evaporation. So at that instant, right, there are no molecules there. Let's say there was vacuum, right, in air, and all of them were liquid. And now what you have here is now you have evaporation, and at the same time there's a little bit of condensation. So that means what you can say here is this, that for B, for example, so let's say this was A, right? So for A, one thing we can say that partial pressure was equals to zero. Okay, partial pressure is how much pressure those molecules that have evaporated, right, they're now basically in their gas form, exert in the container. And obviously, if there were no gas molecules, that means the partial pressure was zero. But now partial pressure basically no longer zero, and it increases. Okay, it increases. And one thing we can say is that now we have this R. Let's this represent the rate at which the those liquid molecules are evaporating. So rate of evaporation is greater than rate of condensation. Okay, that means we can say that the rate of evaporation greater than rate of condensation. Okay, and what we can have here is this process, right? That's going to just continue. Okay, it's going to continue. Now there's another thing that we have, which is it's called the vapor pressure. Okay, so now what is then the vapor pressure? So you can think of, like, let's say the vapor pressure is different from the partial pressure. So let me put here, right, this is partial pressure, which was equals to zero for the state A. Is different, that partial pressure basically represents the pressure at that instant of time at that specific temperature, depending on how many molecules you have. Since we didn't have any gas molecules, partial pressure was zero. But then there's also a vapor pressure. So vapor pressure so let's call this VP. So this is amount of the gas molecules, right? There's water molecules in the air that you can always have at the given temperature, because this is going to be a very specifically temperature dependent. That means at certain temperature you can have, let's say, this amount of a maximum amount of let's say water molecules, and vapor pressure represents the pressure of that maximum amount of molecules that you can have. So for example, vapor pressure at let's say you're going to see, right, let's say that 30 degrees Celsius is it's going to be given in the table. So that's going to be 31 point sorry, the vapor pressure is going to be 4.24 times 10 to the 3 Pascal, for example. So that's going to be vapor pressure. Okay, so we can we can technically get those values in terms of Pascal and also torr. So let's say it's also can be written in terms of torr, because that's also temperature, the pressure measurement. So let's say 31.8 torr. You can also write like this. That means this is given for this particular temperature, because at this particular temperature you have sort of, like, let's say, maximum amount of water molecules you can have in air. Okay. Now, so then what you have is that there's a vapor pressure, which is very specific to certain temperature, and then the partial pressure. Obviously, right now the partial pressure is no longer zero, right, and it increases, and then the rate at which the molecules, the liquid, let's say the or water molecules are evaporating is higher than the rate at which the gas molecules are condensing. Okay. Now, one thing we can have here is as well is that, as you can think, right, at some point the the rate, right, is going to be basically, reach some kind of equilibrium. Okay. So it's going to reach some kind of equilibrium. And that's what we have. So that means eventually we will reach equilibrium. All right. So let's say this is now represents that last state. Okay. So let's say this is going to be then last state. There you go. So now we reach this, condition where um, this is, let's call this state C, where then what we have is that rate of evaporation is equals to rate of condensation. Okay, that means you have equal amount of, molecules evaporating and condensing, which means then, let's say, for example, this vapor pressure, right? So vapor pressure, oh, by the way, here the vapor pressure was greater than partial pressure for the, state B. Okay. Remember, vapor pressure is, let's say, this value, okay, and it doesn't change. Okay. So for state A, when there were no gas molecules, well, vapor pressure 31.8 torr, partial pressure is 0. State B, when you have some molecules, well, vapor pressure is 31.8 still, partial pressure, I don't know, maybe like 10 or 18, whatever it is, but it's less than, uh, uh, let's say, vapor pressure. Then at this point, when you sort of like reach this equilibrium, right, where you have equal amount of water molecules and liquid molecules going back and forth, then vapor pressure is equal to the partial pressure. Okay, so vapor pressure equals partial pressure, and then what we basically have here is this. So humidity is basically defined as the ratio of partial pressure over vapor pressure. And we do like 100 times 100%, so we get percent, humidity. So you can see, right? For example, then for state A, when we had no air molecules, or no, let's say gas molecules, right? There was no evaporation yet. The partial pressure was 0, and divided by, let's say 31.8, which is the vapor pressure. So the humidity was 0%. So there was no humidity at all. Okay. That means for this, we can say that, you get 0% humidity. Okay. For state B, when you had just, some molecules evaporated already, but there were more molecules evaporating than condensing, I don't know, maybe let's say um, it's half, right? So maybe let's say, at this point, you can say that, you have partial pressure is half of the vapor pressure. So then you can say, right, then you can do let's say, um, if you do, the partial pressure divided by vapor pressure, where partial pressure is half of it. Here, let's say you would get something, maybe let's say 50% for that. Okay, so 50% humidity. Maybe that means the air contains half of the amount of the water, the water molecules that it can have. It can have like twice as much, but at that instant it has only half of it. So that's humidity is then 50%. Then right here, when we have our condition C, which is basically now it has, partial pressure is equal to the vapor pressure. That means it has the maximum amount of, the water molecules can contain in the air. Then you can see, right, humidity will be PP over VP times 100%. Then you get, well, 100% humidity. So 100% humidity, when it means that partial pressure is exactly equal to the vapor pressure, and you have the maximum amount of water molecules in the air. Okay, so that's kind of like, in terms of what we have for the um, humidity. Humidity represents that. So what is the amount of the partial pressure, or let's say how much water, molecules that you have, or vapor, how much vapor you have relative to how much you can have as a maximum amount. Okay. All right. So then also we can use basically this, you can say, right, when evaporation and condensation process are in equilibrium, the vapor just above the liquid is said to be also saturated. Okay. That means for state C, we can say that, you know, when this is true, that means the partial pressure and equals to the vapor pressure, then we can say that this is saturated. Okay. So then for the cases A and B, we can say then it's unsaturated. Okay. So A and B, you can say that unsaturated because water molecules in the liquid, state can enter the gas state. So air has not reached the maximum amount of water it can hold. It can hold more water, so it is unsaturated. Okay. So case A doesn't have anything, right? So, but case B it has some, but still it can, you can still have a lot of water molecules evaporating. So we say that it's unsaturated. Okay. So actually, you can even have higher than 100% for humidity. Well, what does it represent? Well, it represents when you start then having higher, let's say if the condensation rate increases your evaporation rate, then you have more, let's say gas to liquid than from liquid to gas. In that case, you can see, right, then partial pressure can actually be higher than the vapor pressure. And then in that, you're going to get something that is a higher than 100%. It can happen if you suddenly, let's say, decrease the temperature. For example, think like this. So let's say right now I have temperature as 30 degrees Celsius. That means the container has a temperature of 30 degrees Celsius. That means my vapor pressure here is, as I said, right, 31.8 torr. Okay. And then I have, like, let's say my partial pressure is also 31.8 torr based on the fact that I have, my maximum amount of, let's say the vapor I can have in that air, right? That means now I have maximum amount of I can have, and then that gives me 31.8 torr. Vp is 31.8 torr based on this specific temperature. But if I decrease the temperature, right? If I decrease the temperature, for example, let's say if I decrease it to 20 degrees, right? That means if I decrease it to 20 degrees, then the Vp is actually 17.5 torr at that temperature. So it's 17.5 torr. But I still have the same amount of, let's say, vapor, right? Still in the air. That means my partial pressure is still 31.8 torr, like this, torr, but my vapor pressure is now down to 17.5. You can do this. You can basically kind of like a quickly to remove the temperature, right? So, and have the partial pressure that is higher than vapor pressure. In this case, you can see, right, if I do the ratio, I'm going to get a number that is higher than 100%. Okay. That means you can have this. This is known as a supersaturated. Okay. So the supersaturated, when the rate of your, then in this case, right, condensation, there you go, is greater than rate of the evaporation. Okay. All right. So here's the table of with all those, values. So you can see that. So the saturated pressure, vapor pressure increases with temperature or decreases with lowering temperature in terms of, right? So you can see, right? So here's the 30 degrees. So those are the values, 31.8 torr or 4.24 times 10 to the 3 Pascal. Okay. So since it's a ratio, probably, doesn't really matter, right? So it's easier to use torr rather than, Pascal, because it's just, easier number, right? So that means you can see, right? So here's a 30 degrees, here's 20 degrees. You can see that in terms of, that's the pressure, right? That's a saturated vapor pressure. That means these are the values of the vapor pressure at those specific temperatures. Another thing we can also have here is saturated vapor density. So how many grams per cubic meter, let's say you take all the vapor that you have, put it on a scale, and this gives you that basically how many, grams per cubic meter you have. Okay. So you can say, right, for example, at 30 degrees, it's 30.4 gram per cubic meters. At 20 degrees, it's 17.2 gram per cubic meters, right? So those are basically the values of the saturated vapor density. So that means we're going to see that we can also have a we can have an equation, right, in terms of the humidity, that we can use this ratio for the let's say in terms of vapor density relative to saturated vapor density. So this is saturated vapor density, which is sort of like a constant at this particular temperature. And then vapor density depends on how much vapor you have at that instant. So similar to that ratio of the partial pressure over the vapor pressure. Okay. So here you can see, right, a liquid boils when its saturated vapor pressure equals the external pressure. Okay. So that means, it will start boiling for, when this condition is satisfied. All right, so let's look at then this equation. You can see, right, the partial pressure, again, it's summarized, is the pressure each component of a mixture of gases would exert if it were the only gas present. Okay. The partial pressure of water in the air can be as low as 0, as we saw that case A, right? And as high as the saturated vapor pressure at that temperature. That's basically case C, where, you reach the equilibrium. So relative humidity is a measure of the saturation of the air. So it's a partial pressure of water divided by saturated vapor pressure of water, okay, and times 100. So that's why, it was 0 for case A. It's somewhere between 0 and 100 for case B. And, let's say they are equal to one another for case C when they're in equilibrium. Okay, that means same way we can also, as I said, right? So we can also use this, in terms of another equation where you have the vapor density divided by the saturated vapor density. That means what is your, let's say the percent relative humidity is also in terms of vapor density that you have relative to the saturated vapor density. That means unsaturated vapor density compared to the saturated vapor density. All right, so let's look at an example here. So from the table 18.12, which is a table that we have, gives the vapor pressure of water at 20 degrees Celsius as 2.33 times 10 to the 3 Pascal. Okay, so use the ideal gas law to calculate the density of water vapor in grams per cubic meter that would create a partial pressure equals to this vapor pressure, and compare the result with the saturated vapor density given in the table. All right, so we are given the temperature and we're given the vapor pressure that we have, right? So saturated vapor pressure that we have at that temperature. So it's asking us to basically use the ideal gas law to calculate the density of water, vapor. That means the density, that means we want to find, like, let's say, how much we have over, some volume, right? So that's, remember, density is mass per volume, or in this case can be like number of moles per volume, right? So we want to find, like, in terms of density of water vapor in gram per cubic meters. So we can find that by first looking at this where PV equals nRT. Okay. So if I rearrange this so that, let's say, divide both sides by V and RT. So V cancels here, RT cancels over there. So I end up with N over V, number of moles per unit volume, which becomes pressure over R times T. Okay. So from here, then I can calculate this N over V, the ratio of number of moles per unit volume, as the pressure that I have, which is 2.33 times 10 to the 3 Pascal, divided by the constant R, which in this case has to be in terms of joules per mole Kelvin. So it has to be the 8.31 joules per mole Kelvin, then times the temperature. Remember, it has to be Kelvin, not Celsius. So 273 plus 20, so 293 Kelvin. So calculating this, we're going to get 0.957 mole per cubic meters. Okay. All right. So, well, at this point, we don't have a way of finding this in terms, like, this doesn't give us like gram per cubic meter, so we have to do one extra step. But at this point, at least we have number of moles per cubic meters. We need to then convert to a density in moles per cubic meters to grams per cubic meters. So then the density is equals to, so we have 0.957 mole per cubic meters. And then this is basically in terms of how much is 1 mole of this, let's say, substance, right? In this case, water. And that's 18 gram per mole. Okay, so 18 gram, that means 1 mole of water, right, is 18 grams. So then here we can see the moles cancel out, and then we have then gram per cubic meter. So this becomes 17.2 gram per cubic meters. That means we got that, right? So for a vapor pressure of water, okay, so we got 17.2 gram per cubic meter. Okay, so then if we go to the table, remember we were at 20 degrees, right? If we go to the table, we can see that at 20 degrees Celsius, the saturated vapor pressure is indeed 17.2 gram per cubic meter. That's basically, we just derived that, right? We derived that quantity from the temperature that we were given and the pressure that we were given, right? So we could see that saturated vapor density indeed is 17.2 gram per cubic meters. All right, so that's kind of what we have. Next, let's talk about in terms of what is a dew point. Okay, so what we have here is then the dew point basically represents in terms of at that specific temperature, right? Is a measurement of sort of like actual moisture that air contains. So in terms of then this dew point, so if you go back and let's say recall that case C, so we can say that when the partial pressure equals the vapor pressure, right? And that's basically the dew. You can say that this is the dew point of the temperature. So the dew point is the temperature at which the air would be saturated with water. Okay. So if the temperature goes below the dew point, then dew, fog, or even rain may occur. And remember, when we say that saturated, that means it has the maximum amount of water vapor it can contain. Okay. So one thing we can do here is then when we, if we cool down, then the condensation will exceed evaporation, right? So as I mentioned already, and so the liquid will start beginning to condense, and then we can have a fog and cloud, right? And precipitation, all that can happen because let's say when you lower the temperature, then you basically, let's say below the dew point, right? Then you can have those, let's say dew fog and the rain and things like that. All right, so here's one more example in this. So calculate the percent relative humidity on a day when the temperature is 25 degrees Celsius and air contains 9.40 gram of water vapor per cubic meters. Okay, so let's do that first, that part. So the calculating the percent relative humidity. All right, so in order for us to calculate the percent relative humidity, we just need to use this equation, right? Where let's say percent relative humidity is equals to. So you can either look at it as the ratio of partial pressure divided by the saturated vapor pressure, or you can look at it in terms of because we're given how much water vapor we have, we can do it in terms of vapor density relative to the saturated vapor density. Okay. So for this one, then we are given that we have 9.4 gram per cubic meters. Then what is the saturated vapor pressure density? Okay. Now, if you go back to the table, you will see that at this specific temperature, the amount of water that we can have cannot exceed 23 gram per cubic meters. So we still have, quite a lot way to go. So that means the relative humidity, we just have, not even half of how much we can have maximum amount. So relative humidity will be 40.9%. Okay. So, well, remember, so technically, if I multiply this by 100%, then I will get that, because it says relative, percent relative. So you have to multiply that by 100%. So you get 40.9%. Okay, that means we have a 40.9% humidity, or percent relative humidity. Part B, it says, at what temperature will this air reach 100% relative humidity? Basically, the saturation density. Okay. This temperature is the dew point. Remember, that means, the saturation, the temperature where you get 100% relative humidity, where then the partial pressure equals to the vapor pressure, or vapor density is equal to the saturated vapor density. That means you have, maximum amount of vapor, let's say molecules in the air. Then that's what we call a dew point. All right. So we can calculate that, um, which is basically going and looking at the table, because one thing we have is that, let's say we do have 9.4 gram of vapor pressure. It says at what temperature will this air reach 100% humidity? We can see that at 25 degrees Celsius, well, it will not reach 100% humidity. At 25 degrees Celsius, it only reaches 40.9%, 40.9% humidity. So if you go back to the table, we can try to see that, what is the, let's say, temperature that can reach 100% humidity with given amount of water vapor. So obviously you can see, right, for the 25 degrees Celsius that we have in this example, right, um, we need 23 gram per cubic meter in order to reach dew point. But we only have 9.4. That means with 9.4, in order for us at that instant to have, let's say dew point or 100% percent relative humidity, we need to decrease the temperature to 10 degrees Celsius. That means if we decrease the temperature to 10 degrees Celsius, that means at that instant, the maximum amount of water vapor we can have is 9.4 gram per cubic meters. And we do have that much, right? We just happen to have that much already. That means we can say that we have reached then dew point of that particular, let's say, amount of water. Okay, that means this is the 10 degree Celsius is the dew point for 9.4 gram per cubic meter, uh, water vapor. Okay, so let's go back then the other part. So that means, let's say that this was part A. Part B is then the temperature is equals to 10 degrees Celsius. Okay, because of that temperature, right? So saturated vapor pressure density, I'll put it like this, is equals to 9.4 gram per cubic meters. So then this ratio will be, so percent relative humidity will be equals to then vapor density over saturated vapor density, just easier to write it like this, times 100%. So then I'm going to get 9.4 over 9.4 times 100. That will give me then 100%, because 9.4 over 9.4 is 1 times 100, I get 100%. All right, so part C is asking then, what is the humidity when the air temperature is 25 degrees Celsius and the dew point is negative 10 degrees Celsius? All right, so let's see what we have. That means we are given that the humidity, um, what is the humidity when the air temperature is 25 degrees Celsius? Okay, but the dew point is negative 10 degrees Celsius. Well, we need to go back and see, let's say, how much, in a way you can think like this information is given so that we can figure out how much of that vapor density we can use. Okay, and since we already know that at the for the humidity or the temperature of 25 degrees Celsius, we need from the table, right, 23 gram per cubic meters. So if we go back again to look at the table, we can see that, all right, so this was at 25 degrees Celsius. And then at negative 10, we can see it's 2.36. That means, let's say if the dew point is here, that means we can have, 2.36. That means, let's say, assuming that for the amount of, let's say, vapor that we have, the dew point is negative 10 degrees Celsius, which in a way tells you how much you have. Because if the dew point for this amount of water vapor that you have is negative 10, that means you have this much, let's say, water vapor. Then we go back and we say, all right, so for part C, that means we are given that there's only 2.36 gram per cubic meters because, dew point of this, let's say, particular amount of, vapor pressure that we have is this much. And then this is then divided by how much it can contain at 25 degrees Celsius, which is again 23 gram per cubic meters. Okay. Then we can see that if we have this much, vapor pressure, or the water vapor, but maximum amount of we can have is that. That means, well, percent relative humidity is then going to be equals to 2.36 divided by 23 is around, let's say times 100%. So roughly 10.3%. Okay, that means 10.3%. That means our humidity will be 10.3 because we are given only 2.36 gram per cubic meter, in a region where it can contain, about 10 times more water molecules. All right, so that was this, the last part of this. Next, we're going to talk about, again, remember, so we are kind of discussing in terms of how the real gas is different from the ideal gases. And this is, another example where in an ideal gas, let's say, model, we don't take the size of those molecules into account. We say that the sizes are too small, so we can treat them more or less like a particle. But obviously, they are not, completely particle, right? They do have a size. And we can think of, like, let's say the closest they can get to one another is from a center to center is this 2r distance, right? That's kind of like a closest they can get to one another. And as they get that close, that means before, when I treated them like a particle like that, but now I'm treating like a spheres, that means this 2r distance is no longer available in a container where these particles are. That means, imagine, right, this much space now, or like, let's say that much space is no longer available. So the volume that I used before should be less than the volume I actually have now, because, some of the volume is occupied by those particles. And that's kind of what we have, right? This van der Waals equation of state takes into account that. So it says, we assume that some fraction B of the volume is unavailable due to the finite size of the molecules. We also expect that the pressure will be reduced by a factor proportional to the square of the density due to the interactions near the walls. Okay, so this gives the van der Waals equation of state, which, contains this constant A and B, those factors, and which are basically experimentally determined, like everything, most of the things in physics, right? So then this equation, right, PV equals nRT, kind of becomes modified, where this is sort of like a P term, right, including the, let's say, the, proportion to the square of the densities, right? And then you have the volume, which takes into account how many molecules or what's the number of moles. Remember, it's just number of moles is just information about how many particles you have, right? How many particles you have. So the volume minus how many particles you have and how much space they occupy. So that means, this equation kind of gives you much more accurate, much more realistic overall volume in your system. All right, so that's why if you look at then the diagram for the that we looked at earlier, remember, so we can see that more or less those diagrams can just slightly shift, right? So you can see, right, you're given it four different temperatures. You have T A, B, C, and D. And from what we looked at before, A, B, C is pretty much identical to what we had, and where this was, remember, that the critical point, right? Beyond which it goes from let's say a gas to a liquid. So most of those, the curves basically fit really nice with the experimental data. The one that a little bit different is the D, right? So the curve D, you can see, right, is below the critical critical point, and passes through this liquid vapor region. So as it goes through that, instead of in the previous graph that we looked at, it goes in like straight without changing its pressure. Here we can see that the pressure actually varies. So you go from increased pressure, decreased pressure, then increased pressure again, a little bit back and forth, right? So that kind of like you have a little more variation in that for that. So you have a maximum point, which is point B, and then you have a minimum point, which is point D over there, right? So you have those 2 points. And um, in terms of, let's say, this kind of like, let's compare to that more theoretical. Remember the theoretical, um, still in a way, when we look at the previous diagram of the real gases, that was still like sort of like a theoretical one, right? So this is a more realistic experimental, let's say, look at the real gases, where the van der Waal equation of state takes into account all those extra space and the densities, things like that, they come into play. Okay, so that's kind of like the differences of those two graphs. All right. So another thing we have here is what we call mean free path. So this is takes into account the motion of the particles. So you can see, right, uh, because now they're not point particles, but they have a finite size. The molecules in a gas undergo frequent collisions, and we've also mentioned that before, right? So even if it's a ideal gas, so the molecules collide with one another, collide with the wall of the container. And what we have here is now that, sort of like, let's say they collide with one particle, and then what is the sort of like a distance they have to travel until they collide again, and collide again. That means, like, let's say how far they have to go in order to collide maybe another particle or another wall. That means, this is what we call mean free path. That means the average distance a molecule travels between collisions. Mean free path, um, generally given with uh, here, like, let's say Lm. Sometimes some books use lambda m for that, but it is, in terms of, you can see, right, we can calculate from the average speed, the density of the gas, the size of the molecules, and the relative speed of colliding molecules. So an equation then becomes 1 over 4 pi square root of 2 r square and n over v. So in this case, what we have here is the v is the velocity, r is the radius. This r is the radius of those particles. So v dt is the distance that they actually travel, let's say. And then in terms of what we can talk about here is n over v. Here is number of particles per unit volume. So you pretty much end up with this equation that can allow you to calculate that average, you know um, average, like, let's say, mean free path. Okay, so here's one equation where this sort of like this lambda over here is basically same as Lm, as I said, right? In some books, that mean free path is pretty much given it in terms of that quantity lambda, which is not the wavelength, but just known as a mean free path. All right, so in terms of then show that mean free path for molecule in an ideal gas at temperature T and pressure P is given as lambda, or the mean free path, equals kt over 2 pi d square and square root of 2. Okay, So, you know, pretty much in terms of like, let's say, looking at deriving that equation for the mean free path. Okay. Now, in terms of then what we have, we kind of given a hint over there, right? Ideal gas at the temperature T and the pressure P. That means you can think of like, let's say, you know, we start with the ideal gas equation, right? So we have a PV equals nRT. We start with that. So then in terms of, let's say, this equation, right? PV equals nRT. Um, so we can look at it in, like, let's say, if you come back over here, remember, so here we're using number of molecules. So in this equation, there's number of moles. So, and we can look at it in terms of this number of moles, if you remember, right? It was number of molecules per Avogadro number. That means it's how much you have, uh, total number of molecules over Avogadro number. That is, you know, what we use for the uh, number of moles. Okay. That means one of the things I can do here is in my ideal gas law equation, uh, I can replace that number of, you know, number of moles with that. So let's say if I have a volume here, and I can say that this is number of moles, sorry, number of moles replaced with number of molecules times RT divided by Avogadro number, like this. And then what I have here is, if I rearrange this, so write it in terms of, let's say, the equation that we have right here, where, let me rewrite that equation over there. So I have, I just call this lambda, right? So Lm, which is same as lambda. So, so this is basically given as 1 over 4 pi square root of 2 r square, then n over v. So this is n over v is number of molecules per unit volume. Okay. And in this equation here, we want to say that lambda is equals to kT over 2 pi, then times pressure, times d squared, then square root of 2. Okay. That means, you know, like, let's say, to show that this is basically equation that we can derive, where d squared is, you know, pretty much same as r squared. Okay. So they're pretty much the same thing. Okay. All right. So now, one thing we can see from here is, let's say we got this equation over here, where I also have a, you know, let's say pressure over there. So PV equals now replacing number of molecules with the number of moles with the number of molecules per Avogadro number. So then if I continue with this, I can say that, okay, then pressure is equals to nRT over V, and then I move the volume here, right? And then I have Avogadro number over here. So from here, then I can take this N over V, which is number of molecules per unit volume. Then I have R over Avogadro number, then times temperature. Okay. Now, one of the things we talked about earlier is that the R, which is the gas constant, it is the, you know, it is equals to Avogadro number of molecules times the Stefan-Boltzmann constant. And that's the Stefan-Boltzmann constant right there. That means if I divide both sides by Na, means that the ratio of R over Na is the Stefan-Boltzmann constant. That means I can replace this with the Stefan-Boltzmann constant, Kb. Okay. All right, so that means we are getting kind of closer. So now I have this equation where P um, equals N over V KB times T. So now I think about this. If I divide both sides KBT, that means that's what my N over V ratio is equals to. N over V ratio equals P over KB times T. Okay. That means what I can do here is, now, so like a final step, take that general equation, okay, and replace this ratio of N over V with P over KBT. Okay. That means lambda is equals to 1 over 4 pi square root of 2 r square, and then N over V becomes then P over KBT, and then KBT goes upward, right? Goes up, so it becomes KBT, then 4 pi times pressure times r square times square root of 2. And that's basically our final answer for that. We can show that I can go from here, the general equation, right? From this general equation to this equation by replacing that, N over V in terms of the pressure and the temperature. That means replacing two of those state variables with another two. All right, so here one more example. Calculate the mean free path of air molecules at the pressure of 3.5 times 10 to the negative 13 atm and the temperature of 300 Kelvin. Model the air molecules as spheres of radius of 2 times 10 to the negative 10 meters. All right, so that means for this, we are given pressure. Let me use a different color here. So we're given the pressure, 3.5 times 10 to the negative 13 atm. We're given the temperature, 300 Kelvin, and we're given the radius, right? 2 times 10 to the negative 10 meters. And now, one of the reasons that I derived that equation for you in the previous example is that we can now use that equation to calculate the mean free path, right? From that equation, because this equals to KT, then 4 pi square root of 2 r squared times pressure. Okay, that means what I can have here is, I don't need to like calculate then N, then V and things like that, because let's say we can see, right, we're not given that from here, but this equation shows that we don't really need that. So from here I can calculate the Boltzmann constant is equals to 1.38 times 10 to the negative 23 joules per Kelvin, then 300 Kelvin, then divided by 4 pi square root of 2, then the radius, which is 2 times 10 to the negative 10 meters squared, then the pressure. Okay, so which is 3.5 times 10 to the negative 13 atm. I cannot keep this in atm because there's a joules over there, which assumes that pressure should be in Pascal. So we need to make that conversion. So we have to convert where 1 atm is 1.013 times 10 to the 5 Pascal. Okay, so then we can cancel that. All right, so calculating everything should give us 1.6 times 10 to the 5 meters. All right, so that's basically, you can see, right? It's a very low pressure, right? It's a very low pressure. So the distance here is insanely high, right? 1.6 times 10 to the 5 meters, which is 160,000 meters, right? But it's a low pressure means that very few molecules, or they're moving very slow. Okay, so this is indeed a very low pressure. Remember, at the room temperature, right? So we have like 1 atm at so like a sea level. All right, so the last thing we have in this chapter is diffusion. So here, so that we can see an example, right? So you have a few drops of food coloring. Let's say you drop it in the water, and eventually you can see it starts spraying out, initially maybe like slowly, but eventually becomes, let's say, you can see, right, initially you can see a little bit of separation between them, but then after some time it becomes pretty much uniform. So that's kind of what we have for the diffusion. So you can see, right, even without stirring, a few drops of dye in water will gradually spread throughout. This process is called diffusion. Okay, And there's actually, a model for that. So that means what you can see here is that it goes always, from one region to another. There's like a direction, and that direction is always goes from region where there's a high concentration to region where there's a low concentration. And diffusion occurs, always in that direction. Always goes from high concentration to low concentration until eventually, you get so like a uniform, system. Okay, but you can see that because there's a sort of like a motion of those, you know, particles, right? Let's say mixture, you can then have some kind of the rate at which that diffusion occurs. So this is that equation, this quantity that we call rate of diffusion, and this is equals to d, which is the diffusion constant, and here's a table where we can see those constants, times a is that, which is the, from here you can see, right, this cross-sectional area, through which this, mixture is moving, and times that dc dx. Okay, so here, in terms of, like, let's say, you can see, right, how the concentration is moving from one region to another region as a function of position. So that's pretty much, what we have in this, in this equation. So that you can see that in terms of the diffusion constant, right, is different for, different type of, molecules. And this, C2 minus C1 here is, that's basically in terms of that, let's say, different in concentration per unit distance. All right, so here's then an example for that. So you have oxygen diffuses from the surface of insects to the interior through tiny tubes called trachea. An average trachea is about 2 millimeter long and has a cross-section area of 2 times 10 to the negative 9 square meters. Assuming the concentration of oxygen inside is half what it is outside in the atmosphere, show that the concentration of oxygen in the air, assuming 21% of oxygen at 20 degrees Celsius, is about 8.7 moles per cubic meters. Then calculate the diffusion rate J and estimate the average time for a molecule to diffuse, um, and assume the diffusion constant is 1 times 10 to the negative 5 meters square per second. Okay, so we can think of it like this. So let's say if you're considering rate of diffusion, so you can think of it like, let's say, to be to the number of molecules, which is, you can use, capital N, right? So number of molecules moving through some cross-sectional area A is a function of time. So J can also be written like that. So number of molecules per unit time. Okay. That means using this equation and using that, equation where J is equals to dA, then dC dx, and then, ideal gas law equation PV equals nRT. So then, we can then solve for the, part A, which says that, show that the, you can see, right, show that the concentration of oxygen in air at 20 degrees Celsius is about 8.7 mole per cubic meters. So we have like 21% of air is oxygen. So we want to show that. Also, we were given in terms of the cross-sectional area. All right, so we start with part A, showing that, let's say, the concentration, right? So the concentration of oxygen in air is 8.7 moles per cubic meter. Okay. So moles per cubic meters is, in a way, means that if I take this equation and divide both sides by N and then by P, both sides, then here I get, cancel the pressure. So then what I end up with, sorry, actually, I'm going to need to do other way around, because I need number of moles per unit volume. All right, so PV equals nRT. So I divide by volume, R and T, both sides. So the volume goes away, RT goes away. So then I have this number of molecules, number of moles per unit volume, then equals P over RT. So when we talk about then pressure, the air pressure, right? So we assume that air pressure is 1 atm. Remember, so at the standard, let's say at the sea level, it's 1 atm. And then we're told that oxygen is 21% of those. That means the pressure that oxygen molecules exert is just basically, 21% of that 1 atm. That means pressure will be 0.21 times atmospheric pressure of 1 atm, which is 1.13 times 10 to the 5 Pascal, then divided by 8.314 joules per mole Kelvin. Then the temperature, which was 20 degrees Celsius, right, ends up being 293 Kelvin. Always must use Kelvin for this calculations. Okay, so now because of now I have only 21% contribution from oxygen to the atmospheric pressure. We can then at this specific temperature we can calculate then N over V to be 8.7, sorry, just 8.7 mole per cubic meters. Excuse me. All right, so that's part A, right? So that's basically for us in terms of the let's say the concentration, right? At that at the temperature. So part B then is asking calculate the diffusion rate J. Okay, that means we can calculate in terms of the what we have is that the concentration is at 20 degrees Celsius, and it says, remember that says assuming the concentration of oxygen inside is half, it is what it is outside, and we calculate what it is outside, 8.7 mole per cubic meters. That means inside is exactly half of that. That means half of 8.73. So that means when we go and for part B calculate then J, since we're talking about in terms of let's say um, oxygen going through let's say some region, and there's outside and inside, right? So the two different concentration. So then we use this this equation over here, D times A, then dc dx, which basically becomes just sort of like, let's say, approximately dA and delta C delta X. Okay, delta C delta X. All right, so we can take then this diffusion constant for air, and for in terms of like, let's say the oxygen, right? So we can take that to be 2 times 10 to the, sorry, 1 times 10 to the negative 5, which is meter square over second. And then we were given that the cross-sectional area A, 2 times 10 to the negative 9 square meters. And then from here, we can look at it in terms of the difference between concentration, 1 and concentration 2. So basically, this is, let's say C2 minus C1, right? C2 minus C1, where we can think of like, let's say the C2 here is the concentration inside and minus the concentration outside. Basically, this is pretty much the difference. So we can, like, let's say even look at it in terms of sort of like absolute value. But the idea here is we have, this is, outside, and inside is exactly half of it. So if I take then 8.7 mole per cubic meters minus half of it, which is like roughly 8.35 mole per cubic meters. So then that's basically, that's what goes here, right? So 8.7 minus 4.35, then divided by the dx, which is the length, and we were given that to be 2 times 10 to the negative 3 meters. So using that, we can say that J here is equals to roughly 4 times 10 to the negative 11 mole per second, which is the equation for the diffusion rate. J for diffusion rate, that means 4 times 10 to the negative 11 mole each second, going from let's say region 1 to region 2, basically between those regions. The last one was asking us estimate the average time for the molecules to diffuse. That means what will be the so this part, remember, so we were also given the diffusion rate here. So estimate the average time for this. As I mentioned, right, there's another equation for the diffusion rate in terms of number of molecules divided by, let's say, by time. So from here, then what we can do here is that if I take then that equation, then rearrange, then becomes T is equals to N over J. Okay. So then this becomes N over, so then J is basically D A, then delta X over delta C, right? So delta C over delta X. Okay. Which then can kind of, be rearranged where I have C here is, which is the, average concentration. So the average concentration, let's take to be roughly number of molecules per unit volume. That's the sort of like an average concentration, where volume is nothing but A times delta X. Okay, A times delta X. And what we can do from here is, I can see, right, if I rearrange, then N is equals to average concentration times, A times delta X. Something like this. All right. So the reason we do that, because then we can rearrange this equation where it's the number of molecules over the concentration rate, where we can replace something like this. If I now use this one over here, if I continue like that, that becomes N times this dx goes up, becomes dx over the constant times area, then times delta C. So then what I can do from here, now replace N with that. Let's use this. So it becomes C average A delta X times another delta X, which is this delta X that was there, then divided by D A delta C. Okay. Then from here, you can see, right, the A cancels out. And then we have C average delta X squared divided by delta C times D. Okay. That means we pretty much, end up with this equation. Okay. And then we can then use this to calculate for the average time. Okay. So that means this is basically roughly what the average time equals to. All right. So we kind of maybe clean it up over here so then we can write it over there. We're running out of room. All right. Then the time is equals to, again, so average concentration times delta X squared divided by delta C times D. Okay. Now, in terms of then, what is average concentration? Well, remember, the concentration that we got is for the inside and outside. That we have two numbers. So this delta C is the difference between them. Average is just then the sum of them divided by 2, right? That means if you have two things, their average is adding them together divided by 2. That means this average is C1 plus C2 divided by 2. That's what it is. Then times delta X squared, then delta C times D. And that's pretty much what we end up with. So this is 8.7 plus 4.35 divided by 2, then times 2 times 10 to the negative 3 meters square, divided then the difference between 8.7 minus 4.35. Just not enough room, so I'm just going to skip the units for now. But then the constant, right? 1 times 10 to the negative 5, diffusion constant, meter square over second. Now, putting everything together, then we can calculate this to be 0.6 seconds. Okay, and that's basically the average time. All right, so this concludes this chapter.